All right, last talk in the day. Hopefully, everyone's still energetic, and we can. And hopefully, this is something that's interesting, which is so what this talk is about. I mean, it's titled Segue, ColorGuard, and Swivel, and it's about optimizing WebAssembly implementations for their performance, scalability, and security. So, for those of you who don't know me, I'm Shravan. I'm a new faculty at UT Austin. And so I'm going to be talking about this for the next 25 minutes. And there's actually a bunch of work over the last few years. All of this represents a bunch of work for the last few years across academia and industry. And honestly, recently, we've gotten even more folks at Intel and Fastly interested with some of this stuff. So even this slide is somewhat incomplete. So this represents the work of a whole bunch of people. And since this is the last talk of the day, in case you've already kind of reached saturation, here's the entire talk in one slide, right? Which is WebAssembly is awesome. We use it to sandbox untrusted code in all sorts of settings. But WebAssembly does come with certain limitations, one of them being performance. You always access your heap or linear memory using a relative offset that has a cost. WebAssembly uses a bunch of tricks with things like guard pages for performance, and this bloats the virtual memory use, and this reduces scalability. And WebAssembly, by its very nature of what it's trying to do, tends to have a hard time blocking Spectre attacks. And this talk is basically about 3 techniques that address each of these in turn. First, I'm going to talk about Segue, which is an optimization of using Intel segmentation to speed up heap access. We're going to talk about ColorGuard, which is an optimization to improve WebAssembly scalability. And we're going to use shiny new hardware extensions like Intel MPK and ARM-NT, basically page coloring of any kind that we can find. And finally, we're going to talk a little bit about Swivel, which is a set of hardening techniques to make WebAssembly resistant to Spectre. And in particular, I'm going to talk about a version of Swivel that relies on Intel CET, which is hardware control flow extensions that are available on new Intel CPUs. So with that summary out of the way, let's get into the details. And of course, we always start with the WebAssembly's awesome slide. So here's mine. Talks about a whole bunch of use cases. But I wanted to dig into one in particular, which is going to be our motivating use case, which is the function as a service or cloud or edge platforms or whatever you want to call it. And the gist of the use case here is that clients are going to submit their computation in the form of WebAssembly files to these edge or function as a service platforms. And function as a service platforms are going to take these WebAssembly files, compile them, and then run them all together in a single process. And really, these platforms are relying on WebAssembly's isolation to ensure different clients' code do not interfere or look at each other, etc. And by doing this, these platforms have eliminated the need for multiple processes. They've eliminated the need for multiple VMs or containers. And by doing these things, scaling really, really, really improves. And instead, you're relying on WebAssembly for all of your isolation. So this raises the simple question, which is, how does WebAssembly enforce this? And I suspect a bunch of you are already familiar with this, but I will quickly go through this just to make sure we're all on the same page. We basically have a couple options. Option 1 is this thing called bounce checks. So if we have a WebAssembly instance with a linear memory of a gig located at 60 to 61 GB in your virtual space, then your WebAssembly engine might generate a code like this to access a portion of this linear memory, which is you have some offset you want to access in this linear memory. You have the base at 60 gigs. You check that the offset's within the size of their linear memory, and then you access it. Perfectly secure way of implementing WebAssembly. Option 2 is this thing called guard pages. It's designed to be a little more performant than this bounce checks. And the idea is rather than allocating a gig, you always reserve 8 gigs of virtual space, the 1 gig of memory you want to use in this case, followed by 7 gigs of guard pages. And this approach takes advantage of WebAssembly's memory 32 format, which basically says all memory accesses have to look like base plus a 32-bit offset plus an optional 32-bit constant as well, which means the most you can ever address is 8 gigs of virtual memory. Which means this approach is also completely secure, even though it does not include a bounce check. And both of these approaches have some trade-offs. Bounce checks don't introduce any funny memory tricks. And so there's no memory overhead per se, which is great, which means you can fill your address space with these 1 gig sandboxes in this example. Unfortunately, they come with a performance overhead. And just to put a number on it, it's about 40 to 100% compared to native code if you implement a piece of code in WebAssembly and run it with bounce checks. And by its very nature, when you have bounce checks, these things tend not to be Spectre safe. In contrast, guard pages trade off virtual memory for performance. It's much faster, and compared to native code, only adds about 20% overhead. It's not perfectly fast because you're still accessing your linear memory with a relative offset, and that has a cost, but it's pretty good. It does come with memory overhead, though, memory bloat, because of this guard page trick. And what this means is you're limited to about 16,000 instances per process. And that's right about at the limit of what some use cases today already are using. So we're going to bump into this limit pretty soon. And even though you don't see a bounce check in the screen, I'm going to assert now that this is not Spectre safe either. And we'll talk about why in a little bit, but just take my word for it that this is not Spectre safe either. So for the rest of this talk, we're going to tackle each of these problems in turn. We're going to talk about Segue to optimize performance, ColorGuard to optimize scalability, Swivel to fix the Spectre attacks. And I'm going to tell you a little bit about some of the ongoing work we have as well, including memory 64 speedups. Just a couple of sentences about that. So diving right in, let's start with Segue. And Segue is about optimizing WebAssembly's access to the linear memory. And the key observation powering this is on x86 platforms, we have this feature called segmentation. Segmentation has actually been around for decades. It's relatively rarely used in today's programs, but the gist of it is you have hardware that lets you specify segments or regions and you can specify the base and bounds. So you could specify a segment GS and the base of 60 gigs and a bound of 1 gig. And whenever you access an offset relative to GS, that offset is checked against the size, and then you're accessing memory relative to the base. This is a nearly perfect instruction for WebAssembly. It's, in fact, you'd be hard-pressed to come up with something better for accessing WebAssembly's linear heap. The challenge, unfortunately, is this instruction in this form went away when we made the transition to 64-bit CPUs in Intel and AMD. So what you instead have is a region which you can specify, for which you can specify a base, but there's no bounce check. And so the question is, well, is that useful? Because WebAssembly relies on the bounce check for security. So what's the point? It's not really useful anymore. And when we did some measurements, we actually had a slightly different conclusion, which is even if you don't have the bounce check, it turns out this set of instructions are super useful because it allows a bunch of optimizations on instruction encodings. And the net result is a pretty significant performance win, actually. And so I'm going to go through one very quick example. And the example is, imagine you have some C code with an integer to pointer conversion, followed by dereferencing that pointer. If you take the C code and compile it using a WebAssembly compiler, you might very reasonably get something that looks like this. So this is low-level assembly code, so you don't have to track everything. The takeaway is you store your linear memory base in a register, you store a pointer in a register, you truncate the register to 32 bits, and then you perform your linear memory access where you add the linear memory base and this 32-bit offset. Very reasonable code generation for this. In contrast, when you do this in Segue, you can do all of that in a single instruction. And there's a bunch of advantages to this. And instead of staring at these low-level instruction encodings, let me just kind of point out the relevant details. One, the existing approaches have an extra instruction, which you can get rid of. Two, the existing approach uses an extra register, which you've completely freed up for your use now because you don't need that to store your linear memory base. And three, the fact that you're using the segment essentially makes it act like a pinned register. And if you remember the first talk from today, we already know that pinned registers tend to speed up sandboxing implementation. So that's in and of itself a win right there. And so we took this idea and went ahead and implemented a prototype in Wasm to C. So Wasm to C is this is the WebAssembly compiler we're actually using to isolate untrusted libraries in Firefox, and this is in production, running on all platforms, including Android. So this is a super important use case for us. And we just ran a subset of the spec benchmark. And what we found is on just like a geo mean, we have a 6% speed up, and this can be higher even. And said in this might seem small, but said another way, speeding up WebAssembly by 6% on this benchmark is eliminating roughly a third to a fifth of the overhead that WebAssembly has on native code, over native code in its guard page implementation, which is pretty significant. And if that's not convincing enough, it turns out this sort of instruction code generation reduces your binary size a ton as well. And due to these advantages, Segue has actually already been adopted by WAMR. So folks at WAMR have gone ahead and implemented this, and in fact, it's on by default, improves the performance, improves like the code generation size, and interestingly, apparently reduces the compilation time as well, which is interesting news to me too. So we'll have to get to the bottom of why that is at some point. And I do have additional plans to also upstream this to Wasm to speed up this Firefox library sandboxing use case as well. So that's the whirlwind tour of optimizing performance. Let's jump to the next bit now, which is scalability. Now, the core problem of WebAssembly scalability is guard pages. Guard pages have a cost on virtual memory space. So if you just create a couple of WebAssembly instances, you've already lost 16 gigs of virtual space. So what the ColorGuard optimization says is, well, let's just get rid of those guard pages. Go ahead and put your WebAssembly instances back to back, except we're going to give each of them a unique color. And you're going to do these colors with things like Intel MPK and ARM MTE. And as you go ahead and do this, you're going to very quickly run into a limitation, which is the number of colors you have in any of these platforms are limited. So it's usually in the order of 8 or 16 or something. So you're going to run out of colors pretty soon. So what do you do when you run out of colors? Well, ColorGuard gives you a very simple answer, which is you can go ahead and reuse colors. You only need unique colors for about 8 gigs. And the reason for this is, if you remember, WebAssembly's memory instructions, at least 32-bit ones, can only access 8 gigs of virtual space. So you only care about unique colors in that space. And effectively, with this construction, instances B to H acts as the guard pages for instance A, even though you've never actually wasted space on guard pages. So you kind of get the best of both worlds, performance of guard pages without the bloat. And we did a couple of measurements on how this improves the scaling and, for that matter, even performance of WebAssembly engines. So we did this simple prototype in Wasm time where we instantiated a whole bunch of 1 gig Wasm instances with guard pages and with ColorGuard. And obviously, we see a huge scaling improvement because we don't waste a ton of virtual space. But interestingly, and perhaps even more interestingly, which is we actually see a performance improvement. And to think about the performance improvement, think about destroying a whole bunch of WebAssembly instances, in one shot. If you have guard pages, the way you'd go about doing this is destroy one, then destroy the next, destroy the third, etc., because these are not contiguous in memory. The actual linear memories are separated by guard pages. And on average, that costs about 25 microseconds. But once you have them back to back, you can actually batch this process in a single destroy call. That saves you about 8% of performance right there, which again is a pretty substantial win when this is something you're doing tens of thousands of times per second, as is done in edge platforms. So again, because of all these benefits, there's ongoing work to get a production quality version of ColorGuard in Wasm time. And there's a whole bunch of folks at Intel and Fastly who are actually heading this up. I put the names of a couple of people you can talk to in case you're curious about this. But this is also something super exciting for us because this is all kind of hot off the press, research presses, and it's already hitting production hopefully pretty soon. So, all right. We improved scalability, improved performance. Next up, Spectre. So what is this issue of Spectre and why are we worried about it? Well, the very short version is Spectre allows you to break out of the sandbox. And to show you how, let's go back to our running use case of the fuzz function as a service platform. And now we're going to run code from 2 clients. client A and client B. They both have their own WebAssembly instance. And we're going to assume client A is malicious and is trying to read the data of client B. Let's also go ahead and assume that this WebAssembly engine is executing this code with bounce checks. So we're going to, pseudocode roughly have something that executes like this, which is if your address is in your linear memory, you are allowed to dereference it. If not, you aren't. Now, this is fine when you execute this concretely, but when this is executed speculatively, the branch predictor kicks in, right? And when the branch predictor gets an incorrect prediction, you're essentially going to perform a memory access here of an address which isn't in the linear memory. And there's a little bit of additional steps to kind of, figure out how to get this data and leak it correctly, etc. But let's leave that out for now. This itself is already a problem, is what I'm going to say. And this is actually an example of a particular version of, the end result of all of this is, of course, you can access the memory of another client, which is exactly what you want to prevent. And so this is actually an example of a version of Spectre called Spectre PhD, which I can summarize as branches will lie to you. They can and will lie to you. And in fact, these are not the only conditional branches in WebAssembly engines. It turns out conditional branches also exist for things like indirect function calls in WebAssembly, because you need to perform a function signature check. It turns out most WebAssembly engines also have a few branches when you grow your stack to make sure you're not growing your stack by too much. And there's a couple other places as well. So they're scattered here and there. And it's not just the conditional branches even, because there are a few other versions of Spectre. So we talked about Spectre PhD, which is branches lie to you. We also have Spectre BTB, which basically can be summarized as your jumps and indirect function calls are completely random. They can go anywhere they want. And we also have Spectre RSB, which basically the same thing for return instructions. Return instructions are random. They can go anywhere they want. And there are a few additional variants as well, but let's just talk about these three. This is interesting enough as is. So with this setup, simple question: how do we solve this? And for general programs, I'll be the first one to tell you, I don't know. There's a whole bunch of smart people working on it. We haven't really found a solution that we're ready to deploy in production everywhere yet. So whatever we come up with is likely going to be specific to WebAssembly and going to take advantage of WebAssembly properties. So in particular, for WebAssembly, we can state a very succinct property we want. We want to stop sandboxes from breaking out of their own linear memory. Essentially, we can allow any speculation. In fact, we want to do this because we don't want to restrict performance, but stop the speculation the moment the code accesses memory other than your local linear memories. So the obvious thing you could try is, well, can we insert a whole bunch of fences in the code to eliminate like bad speculation, etc. And so we tried. We tried implementing fences after loads, fences at control flow targets, fences optimally inserted according to a min-cut algorithm for the least number of fences, using clever algorithms, essentially. And the takeaway is we're talking about performance overheads in multiples, which isn't great. So let's leave these fence solutions on the side. They're not quite doing what we want, but we can come back to them. So rather than going with these fence-based approaches, let's see what hardware can do for us. And so the approach I'm going to tell you about is one version of Swivel called Swivel CET, which takes advantage of new hardware. So this is all from like work that we published a couple years ago at this point. And this is one of many schemes we proposed in that paper to harden WebAssembly. And I've adjusted it slightly from the original paper. But I think this is the scheme that really is relatively simple to implement. And what it takes is essentially three things. You want three modifications in your compilers. First, you want all of your branches and runtime conditional checks to use speculative load hardening. And this is a well-known technique. Basically says, make sure the data in your branches is conditioned on explicitly has a data dependency on the condition. And when you do this, it eliminates, you can take my word for it that this eliminates like memory accesses to bad addresses because the branch predictor got the prediction wrong, etc. The second thing you want to do is go ahead and enable this new extension CET on the WebAssembly generated code. And finally, the third thing you want to do is implement this custom construct we've come up called the register interlock, which is basically a fancy name for a speculation-safe CFI, which is specifically suited for Wasm. And I'll get into what that is in a second. But let's start with these two things, because roughly speaking, we know what these things do. And I kind of wanted to show you what this does to the security guarantees of the code. So if we take just these first two properties, enable SLH, enable CET, and go back to the 3 versions of Spectre, let's see what happens. So for Spectre PHT, we know that we're hardening branches. So basically, misspeculations can't result in memory accesses outside your linear memory. High level, this looks great. So this is, let's say that this is not an issue for now. Then I'm actually going to jump to Spectre RSP and see and point out that because we're enabling CET, specifically the subset of CET which has a shadow stack, we actually get safety because if we actually read Intel's documentation about the shadow stack, it explicitly states that if there is misspeculation on the return address, speculation stops. So this actually completely solves the Spectre RSP problem, which is fantastic. So we don't have to worry about this. So what we're left at this point is Spectre BTD. And for this, we have enabled the CET end branch instruction, which to summarize essentially means that indirect jumps can't go anywhere they want, but rather they're restricted to function entry points and the arms of switch tables effectively. And this is pretty good. But the question is this safe? And the answer, no, not really. Because end branch targets, yes, you've restricted the number of targets a lot, but you still have multiple targets, and these targets may have gadgets. So the easiest way I can show you how this is going to actually play out is by showing you some code. So I'm going to show you 2 functions now, which are very reasonably the output of WebAssembly engines. The first one, foo, stores a random value in a local variable ret, which let's say is mapped to a register RAX at the assembly level. It then has a switch table. And of course, the arms of each of these switch table, the cases of these switch tables have end branches because we've added CET. And this is a perfectly reasonable function, nothing weird with it at all. And I'm going to talk about, and then now let's look at a second function, bar, which is trying to dereference an offset in the linear memory. The linear memory, let's say, the address is stored in the register RAX. And this has a switch table too. And in case 1, it's going to access RAX plus this 32-bit offset. Again, perfectly safe. Let's assume guard pages exist and everything's set up correctly. This function is perfectly safe. But when you have both of these in a single WebAssembly instance, you could have this switch table speculating into a target of the second switch table. And if you trace this code execution through from the top of foo to the bottom of bar, you now see that you've essentially dereferenced the piece of memory with a completely random location. Not in your linear memory, but at a random location. So this is what I mean when I say targets can have gadgets. So what we really want is to prevent this sort of speculation. And we want to prevent it with this register interlock, which is a speculation-safe CFI for WebAssembly. So let's think about it abstractly. If we do have a speculation-safe CFI, what we'd want is something like this, which is in function foo, we would set a unique label. And in the arms of the switch statement, we'd check that label. In function bar, we'd have a unique label as well. And in the arms of the switch statement there, you'd check that too. So this is all hopefully straightforward. Hopefully everyone's following this. Now, the crux of the question here is, how do you implement this? So it's actually not that hard. You need a little bit of setup, which is you need to reserve a register. It has to be reserved for your CFI labels. I'm going to use R10. And you're going to keep locations 0 to 4 GB in your virtual space unmapped. This is just a shortcut for now. You can maybe avoid this in the future, but let's go with this. At which point your set interlock label is actually super simple. You just assign your label to your register. That's it. The check interlock label, on the other hand, is going to set up a data dependency, just like SLH. You're going to set up a data dependency for your heap base and your stack pointer. depending on the CFI label. And all of this is with straight line code, by the way. And I'll let you think about this offline, why this works. But the intuition is if you set up a data dependency for any possible memory you can access, which you can do because WebAssembly has a heap base and a stack pointer, well, you can't really access any useful memory speculative when you misspeculate. That's the intuition. So with this in place, what is the performance hit? Because this is additional code, there is going to be a performance hit. Now, I wish I could give you the most accurate numbers for this, but the best I have are slightly out-of-date numbers, unfortunately. It's still, some of this is all fresh off the presses, and so I can't give you the best numbers. What I can give you is some numbers from a couple of years ago where we had a more complicated scheme, and that scheme, in this context, represents an upper bound of the real costs. And we ran this on a subset of spec benchmarks again. And what we found, the green bar is what you want to pay attention to here. What we found is there are a lot of benchmarks where the overhead is pretty small, like a few percent, that's it. There are these couple of major edge cases as well, of like 200%, etc. But broadly, these beat out all the fence solutions by quite a lot. And we're still working on getting rid of the 200. No one wants 200% overhead. We'd be much happier if this was closer to 10. So let's see if we can actually get there. Some of this is ongoing work. So with all of this, with all of these optimizations, we also are looking at a few additional steps to make all of this work well. And one of the big things we're working on right now is how do we optimize the implementations of Memory 64? Because a lot of the stuff I've been talking about is specific to Memory 32. And the core of the problem with Memory 64 is guard pages no longer work on 64-bit systems to implement Memory 64. So you're stuck with slow bounce checks. And so we actually have an idea that we can do better than bounce checks. And I would love to get into the details of this approach, but I think I'm already at the limit of time I can spend at this talk. So I will save this for a future date. But our early results are promising. It does say that we can actually do better than bounce checks in a completely platform-neutral way. The next steps we have here is I want to look at platform-specific optimizations too. And so for this, I have an ask for anyone who's around who might have a CPU with MTE. If you have a CPU with MTE that you can have a link to share and letting me run some benchmarks on it, that would be super useful. Please reach out. This would be tremendously helpful. So let me know. And the other question is, how do we that we're working on is how do we combine all these optimizations? We've talked about 3 or 4 optimizations here. It's not always clear you can put them all together with no issues. And so that's another thing we're kind of targeting to make sure all of this plays well with each other. So quick summary. WebAssembly is awesome. We rely on it to sandbox untrusted code in a bunch of places. It has some limitations on performance, virtual memory bloat, and Spectre safety. But it turns out if we leverage the right hardware, we actually are in a pretty reasonable shape to actually tackle these problems and improve on the performance and the scalability and actually tackle Spectre safety for WebAssembly. So thank you for your attention. I'm happy to take any questions.
Hear the applause. Great. Do we have any questions in the room?
Hi, Daniel here from the VA team. Thanks a lot for the talk. Cool stuff. So I have 2 questions. One question is about Segue and about platform compatibility. So the GS and FS segment-based registers are often used for the thread information block on Windows and for thread local storage on Linux. So how does that work? Like, is that platform compatible?
Yeah, so that's a great question. So it is indeed used for thread local storage. By default on applications on Linux, FS is used for thread local storage. On Windows, I think it's GS. Technically, they both leave the other one unused. And that's a little bit of a hand wave because that's not fully true. But on Linux, by and large, that's true. So you have one segment that's unused, and you can go ahead and use it for Segue while not messing with your thread local storage. Now, there are lots of exceptions to this. For example, as in the SGX environment, both are used for different reasons. In certain Windows cases, you need both for certain structured exceptions, etc. So you do have to be clever about when you have this available. But at worst, if you're willing to spill and unspill the segment register, you can always use it.
Okay. I would be particularly interested about the Windows use case, naturally, because of the user base that that Chrome has. So maybe we can take this offline.
Absolutely.
Oh, I have a similar question about that too. So one of the issues with tail calls is that anything that's live and registers across calls, you need to restore in a way. Is it expensive to restore the segment registers in a way that might make tail calls slow?
So it does. I can't speak to how exactly it affects tail calls, but I'm sure you can. I think you can fill that in with maybe this little bit of information I can share, which is it is a little bit more expensive to update the segment register than a conventional register. I'm trying to remember the numbers off the top of my head, and I wouldn't trust these numbers because it's working from my working memory, but it's closer to 10 to 15 cycles rather than the one you might get to update a register. So maybe that can help you factor it in. You don't want to be in a position where you're updating this a lot. You can imagine that if you have multiple WebAssembly modules, you update this every time you enter one module because they have their own linear memories, and that might be okay, but I would hesitate to update it every function call. So you could, but look, there's a trade-off here. You can imagine that you can use Segue for functions that don't use tail calls and fall back to using the conventional register-based approach for linear memories on functions that do use tail calls. You don't have to be uniform across your binary.
Just off the top of my head, you probably want to actually do that conditionally, and so you'd have a well-predicted branch.
Yeah, very possible. And actually, that would be reasonable too from a Spectre perspective because either side of the branch is safe. So.
Yet another question on memory 64. You mentioned something is coming up and you don't want to spill the beans, but maybe can you spill a bit of the beans? So what exactly are you doing? Does it have to do with like second level address translation or like what are you doing? Like just some terms?
In the interest of my own research publication future, I'm going to take the fifth on that. But the short version is, look, we were trying to get rid of the bounce checks. You have to figure out an alternative to the bounce check instruction. And we are playing with alternatives, playing with alternate instructions that effectively act as bounce checks in that they will stop you from going out of bounds, but are not explicit bounce checks. The reason I'm also hesitating is not really because of any publication reason. It's because these numbers are a little fresh off the presses. It's literally from a day or two ago. So I also kind of want this to settle down a bit and run this on spec. All of these are run on smaller benchmarks. And I want to run these on bigger benchmarks before I kind of announce it. I'll just say for now that it looks promising. We do think we can do better than memory 64.
Sure.
Better
yeah,
than
no worries. I mean, I can fetch you in 2 weeks and then ask again.
Sounds good.
Just a reminder, you are among friends.
Fair enough.
Question about multiple memories. So I assume, there's a few strategies for implementing multi-memory, right? One is to pin memory 0 and assume that's like the best one, and then the others are going to be slower, or you could just register allocate your whatever. I assume for the Segue stuff, it's just an absolute win over any of the strategies that aren't using it. So if you were to pin register 0, now you just use put your memory 0 in the segment register. If you're going to register allocate them, maybe you still pin memory 0, but you now have an extra register for all your other stuff. So that's still better.
Exactly.
But is there any way to make like all your memories fast?
Sadly, not with the hardware, not without hardware changes. So if we imagine we had segmentation as existed in 32 bits, one of the other things that 32-bit segmentation had was the ability to pick one of your many segments. So you could set up different segments for different memories and just swap between them by writing to your segment selector, which is just the register as well. And it's pretty quick to update, actually. The reality is Intel and AMD have not implemented that version of segmentation for 64-bit. And even if they did, it would now show up only on the newest CPUs. And they have reasons not to. It turns out this is microarchitecturally very hard to maintain, and there's a huge cost for them. I assume. I mean, this is my best guess for it, at least. So the short answer is no. There is another thing another research talk which I've given from time to time. Maybe some of you in the room have seen it, which is called 8 to 5, which is what is the minimum hardware extension CPUs can add to speed up WebAssembly. And this tackles that problem a little more directly with hopefully a microarchitectural implementation that is a little easier than full-on segmentation for CPU vendors. So another side project of mine is to try to talk to hardware vendors and figure out, it's a main project, probably shouldn't call it a side project, and actually figure out how to get that incorporated into CPUs so that we have something reasonable for multiple memories, something reasonable for 64-bit memories, and so on. But yeah, short answer, we don't have anything concrete with our CPUs today.
Cool, thanks.